Hey, George, you're a scientist.
I'm a chemist, yes.
Right, you're a scientist. So, like, how does a microwave actually work? And I say actually work because I am of the generation where I remember two things that, upon scrutiny, don't seem like they're entirely true. They may be partially true for like some weird reason, but I doubt this is the whole story. One of them is the one that I'm pretty sure is just not true at all because it would be like magic. It heats from the inside out, which just always, it was one of those things I remember hearing as a kid and then later being like, wait, no, that doesn't make any damn sense. And then
how would it do that?
it's magic. The M in microwave is for magic.
Mm-hmm.
And then the other one is that it is specially tuned so that the energy it emits, the microwaves, only heat water. And the thing that I like remember hearing that, and it's like, oh, but if you put something really dry, like a ginger snap cookie in, if you put it in for like a minute, it doesn't get very hot because it doesn't have a lot of moisture in it. And that's one of those things where it's like, okay, all of those things are like, you can't observe them as evidence, right? Like, I put this thing in there, it does not have a lot of moisture, it did not get really hot, but it does not follow on from that automatically microwaves only are tuned to heat water. So how does a microwave actually work?
Darn it, Lions. I'm a chemist, not an engineer, but with my very limited expertise and very limited knowledge set, I will attempt to apply to this. So, to your point, right, is that is one of those things that absolutely. So the first thing's just banana. That's wrong. I mean, it would work if you put a microwave emitter inside of the thing that you're trying to heat up, and then definitely
right.
heat from the inside
we
out.
did it. We made it technically true.
I made a really hot duck and I put it inside of a turkey, and ta-da. Anyways, the water thing though, that sounds right? But here's a thought experiment for you, right? Is that if you put does butter have a lot of water in it? Not just butter, right?
I mean, butter's lipids, so no.
Right, but it'll melt if you put it in the microwave, right?
Yes.
Yeah. And like corn oil or like oil that is.
Yeah.
That will melt. That will heat.
Which I believe we discussed famously, not mixed with a lot of water.
Does not mix with water, right? So so if you put oils in the microwave, which do not have water in them, so they are dry, right? They will also heat, albeit slower, right? So that was the thing, and that's actually part of why I added this one to the list, because I was like, I know that that's wrong, but I want to figure out what it is, right? So like, because it's common. It's like, oh, well, it heats water, and here's the thing: is that there's, just like with all good lies, there's a lot of truth to it, but it's not quite right? So this is, hopefully by the end of this, all of our listeners will have enough information to be a total drip at a party, and like,
I think you mean the star of the show.
Oh, absolutely, right? In their minds, right? So, as always, if we're going to bake a pie, we must first make the universe. So, what is heat?
It's the measure of activity in a system.
Well done, man. Hell yeah.
We've been friends for a minute.
Yes. 99% of the way there. It is the measure of the kinetic energy in a system.
Yeah, I said that. You just dropped out on the word kinetic.
Oh, man, if only we had a recording or something.
Yeah, no, we don't, though.
As you're like frantically deleting the way you said. That's true. You could just edit yourself in saying exactly what I said, and then I'd sound like a huge tool.
Yep. Not gonna, but I could.
So yes, it is the measure of the kinetic energy in a system. So, and let's see if you can remember this from high school or middle school science. How do we transfer heat?
Through radiation?
That's one of them. Yep.
Okay. Contact?
Yeah. Yep. That's another one. That's conduction. Yep.
Yeah.
So you remember it was conduction, something,
convection.
Radiation. Yeah. Yep. Conduction, convection, and radiation.
Yeah.
And this actually was like a side little project that I ran to ground, and I wasn't happy with it, but I was like, because they were always like conduction, convection, and radiation, and I'm like, So conduction makes sense, right? You put a hot thing against another hot thing, it transfers the kinetic energy through heat. That makes sense, right? Radiation makes sense. It's light. But like convection means it's like you're heating something up and then it heats the fluid, air, water, or whatever above it. And then those fluid molecules, right, that are heated travel upwards, heating everything around it. And then like they start to cool off and they come back down, right? As they've transferred the heat to their surroundings. That's touching, man. That's just conduction with extra steps. Like, and that always bothered me. Like, not always, but like, I don't know, for like the last like probably 15 years, I'm like, no, why are we carving out this special thing for convection? Like it's just touching. And so I did some work on it. And I can't find a super satisfying answer. So it seems like that it seems like when it's still being taught in high school chemistry or whatever, it's still conduction, convection, and radiation. But when I was looking at like more like higher level scientific descriptions, they tend to describe convection as like a type of movement, not as a type of heat transfer, right? So it's like convective currents, And so like that transfers heat. So it's like convection is kind of like a type of conduction, right? But it's easier to just say like, oh, well, there's so many things where convection is so important that they kind of like made it its own thing. But I'm like, it's not being transferred through photons. And then I went way down the rabbit hole where I was like, okay, well, but electromagnetic radiation is also technically touching because the photons are hitting the thing. So I was like, so then it's all conduction. And then what am I doing to this taxonomy? And I guess it's all three still, whatever. So
is it, could it be that it's like a difference in like efficiency or like magnitude or throughput, right? Because like if you have like a solid block of iron that is very hot and you press it against someone's face, like say a stoolie, like you press it against the stoolie's face directly,
yeah,
that would conduct way more heat than if you put it near their face and it's heating the air and then the air is touching them.
Yeah, I mean,
like if you wanted to torture this stoolie, you would definitely go to like full blown conduction.
Well, and there's actually so there are equations to describe what you're saying, right? So basically, there's the coefficient of thermal conduction, I believe, or something like that. But basically, it says like how effectively does this thing transfer heat from one thing to another, right? So I think that would, using those equations, that would still probably work. But I think that the thing is that it's just what I eventually came to is there is some value to separating these two things out. So like I can quibble through words and concepts and say technically these two things are the same thing, but there must be some value in saying like, no, this was done via a solid thing. And what I started to lean towards, and I didn't quite get there, which was conduction is a solid thing touching another solid thing. Convection is a solid thing touching a liquid thing, where it's like the liquid is transferring it. And I was like, maybe that's it. I don't know. I didn't come up with a satisfying thing, but I still was like, no, math is math. Touching is touching.
To bring this back to cooking, I think the amount of throughput actually might be the differentiator, because like a convection oven heats the air and like circulates the air so that the thing you're cooking, right, your Christmas goose, is getting heated somewhat evenly from all sides. Whereas if you put your frozen Christmas goose directly onto like a cast iron plate that was very hot, the bottom would get very crispy and burnt and the top would still be frozen. So like maybe it is like a throughput thing.
Yeah, it might be. I think that because one of the things I found recently is I don't like to use it with cooking. Cooking actually makes up some of its own terms that are then sometimes used by people thinking that they're science terms. Like, for instance, vegetable is not a science term. It's a cooking term, like,
yes.
Where somebody's like, that's a vegetable. That's a stalk. That's a vegetable. It's like, no, that's a fruit, like it's anyway. So, didn't come to a satisfying thing, but thank you for taking that little journey with me. Microwaves, right, are between radio and infrared rays in energy, right? So they're not heat rays, they're not radio, where we do radioactivity. And so it creates an electromagnetic field, right? So we actually spoke briefly in another podcast about the fact that, inside of a nucleus, right, you have like the positive protons, and outside the nucleus you have the negative electrons, right? But so what happens, let's just say, if you had like a magnet, right, or in this case like an electric charge, right? What would happen if you put like the opposing charge towards it?
You mean like a positive magnet and a negative magnet?
Yeah.
They attract.
Exactly, right? So like let's say though, if you were to take that positive magnet and you were to just do a drive-by on the negative side, right? What would happen?
You talking about like you can get things like kind of spinning in like a certain orientation?
If you just run it by there real fast, right?
Yeah.
If you were to like, let's just say like have a wave and like throw it past there real fast, right? The magnet would start to spin, right? Well, as we spoke about why oil and water don't mix, why don't oil and water mix?
Because the different side molecules are like they don't bond, they repel each other.
Well, because water is polar, right? Water has a charge to it, right?
Slightly, yeah.
Yes, it has because that's the thing is it's not like
it doesn't take
sodium
much.
chloride, right? Yeah, it's got a dipole, what's called a dipole moment, right? So like the oxygen is a big hungry atom, and it demands all of the electrons, and hydrogen's like, okay, man, it's cool. I'm just happy to be bonded to you. I'm just, I was all by myself. It was terrible, right? I got ejected from a star, and now I'm just like happy to be in like a stable relationship, right? So it's happy giving up its electrons. So the hungry oxygen has a slight negative charge, and the water has a slight positive charge to it, right? So if all of a sudden you start putting electromagnetic waves past that, it will start to spin, right? The water molecule will start to spin. And by the act of it spinning, that is increasing the amount of kinetic energy in the system. So it then transfers some of that energy to the stuff around it, right? So it actually heats anything with a dipole moment, anything that is slightly polar, and it heats more stuff that is more polar, right? So fats actually do have some polar stuff on them, as do sugars, right? So those will heat and start spinning, but the thing that has the biggest dipole moment out of those three is water. So it heats water most effectively, but it will heat fats and sugars as well. So the whole like, oh, let's attune to water. It's like, I mean, a little,
kind of,
because there's a whole bunch of like stuff that has that dipole moment to it, and especially when you get into broader strokes of chemistry, there's wild stuff that has like dipole moments. But when you think about stuff that's in food, it's like, well, it's either a carbohydrate, which has some dipole moment to it, but not a lot, a fat, which has some dipole moment to it, not a lot, or water, which has a large dipole moment. So it is by far the most effective, which is why it heats the most effectively.
So this is a fantastic example of, like on the macro scale, we use terms that technically may have like a relationship to their scientific counterpart, but so the microwaves bombard these things that are tuned to be positively charged, right? Go by and smack them, make them spin. So technically the heat is being generated by kinetic energy.
Well, and also yes. Well, and also too, just to be more specific, is that they're not attuned to that. All electromagnetic radiation would do that, right? So
sure.
It's just that they're specifically bombarding it with that type of radiation and an intense amount of it to get it spinning. Yeah.
But this on a macro scale, like on a human size scale, when you think of like kinetic energy, you think of like stuff bodies do, right?
Right.
And if you just like say use a cricket bat to beat the crap out of your Christmas goose, like you are imparting a lot of kinetic energy into it, but probably not enough to cook it.
Well, that's the thing, is that you're imparting too much kinetic energy into it, right? So the kinetic energy, because I mean, technically, right, you could slap a turkey enough to heat it up, to cook a turkey. That's technically possible, right? Like, would it ever happen? No, but you could slap a turkey till it's cooked, And just like Homer Simpson says, it's like, I didn't say they couldn't, I said you shouldn't, right? Which is really interesting, right? Because kinetic energy is just energy in motion, and its corollary is potential energy, right? So like in chemistry, where we normally see that is, it's like, well, how do you say it? So in physics, right, it's like kinetic energy is when I'm swinging the baseball bat, right? and actually cricket bat. And kinetic energy is also when I'm winding up the cricket bat. But when I'm fully wound up and ready to go, right, that's all stored as like potential energy. And then as it swings downward, right, I release it as kinetic energy, right? The same thing with like a swing. When you pull it way up and hold it, now you're spending kinetic energy into the system that it is now storing as potential energy, and then you let it go and it flies out. What we normally think of it is potential energy is stored in bonds, and kinetic energy is just all willy-nilly, right? It's released. So how well something stores potential energy and then can access it as kinetic energy is really interesting. This is completely a field of what we're kind of talking about, but like one of the best ways our body can get potential energy into kinetic energy is through adenosine triphosphate, or ATP, right? So the nice thing is that it stores potential energy pretty good and can transfer it well into kinetic energy, but it's not very energy dense. So that's why we have like glucose and cellulose and fats and all of this other sort of stuff in the body. So that's has way more potential energy per unit, right? But it's not as easily accessible, right? So that's why our body has like, Schrute bucks in between the Stanley Nichols and unicorns, right? So
what an analogy to grab.
Because it forces that middle ground, but that's also why like we die if we don't breathe for like 5 minutes. It's because our body ceases to be able to break down ATP into ADP, and then it just expires. So you're always about 3 minutes away from death, and taking a breath resets that death timer. So
is the ATP thing, is that the Krebs cycle?
Yeah. Mm-hmm.
Oh man, I just made like my junior year anatomy and physiology teacher super happy, which does remind me of another thing I want to ask you about.